All right, hello and welcome. My name is Jared Cohen. I'm the Marketing Communications Manager for Parker Chomerics. This is the Introduction to Electrically Conductive Adhesives and Sealants webinar. Welcome, everyone. I see folks are still joining us, so we'll give them another 10 or 15 seconds before we begin. Thank you. All right, I think folks are starting to come in and we can start. So just a few housekeeping details before we begin. Please set yourself to listen-only mode if you aren't already. You should have joined in listen-only mode. One of the main features of this webinar will be the ability to ask questions during our question and answer feature at the end. So please go ahead, see that Q&A button on that bottom ribbon there. Go ahead, submit your questions for our experts during the webinar. As you may come across your question, go ahead and submit it. Submit as many as you'd like, and we'll try to get to those at the end. And finally, this webinar will be recorded and the link will be sent to you within 24 hours. So if you have to hop off, if you want to watch it again, no worries at all. You will get this automatically. All right, so let's introduce today's speakers. We have Sierra Eiden, Ben Nudelman, and Brian Flaherty from Chomerics. Sierra, are you there?
Yeah, hi. Thanks you guys for joining. My name is Sierra Eiden, and I am a mechanical engineer. Been doing technical sales for Chomerics for over 10 years now.
Hello, everyone. My name is Ben Nudelman. I'm a market development engineer for Chomerics, and I've been with the team for about 3.5 years.
Hello, everyone. This is Brian Flaherty. I'm the Specialty Materials Product Line Manager. I've been with Parker for over 20 plus years, developing, testing, and selling a lot of these conductive materials that we're going to be talking about today.
Excellent. All right, so we'll go into the agenda. We'll first touch briefly about who Chomerics is, and then we'll go into the basics of electrically conductive adhesives and sealants. We'll discuss the design considerations as well as working with and dispensing these compounds. And finally, we'll end with a few case studies that I think you'll find really enjoyable, and we'll have that time for that question and answer at the end of the webinar. So like I said just before, see that Q&A button down at the bottom. Go ahead and submit those questions if you have them. All right. So a little about Chomerics. Parker Chomerics is a division of Parker Hannifin Corporation, and we are the global leader in the development and application of EMI shielding compounds, materials like we'll talk about today, as well as thermal interface materials. Our core competencies are in material science and process technology. And at Chomerics, we really do offer a market-driven sort of product development cycle where we feature integrated electronics housings, and we're really proud to offer a true custom engineered solutions as well as integrated global supply chain management for all of our customers. So with that, Ben, I think we're ready to begin.
So to start, let's get into some of the basics of what makes up a conductive sealant or adhesive. In most cases, there are two main components, a base polymer or binder and an electrically conductive filler. The binder is usually one of a number of polymers that accounts for many of the physical properties of the compound, such as the adhesive strength, flexibility, and working life. The conductive filler, on the other hand, consists of a metallic particle that is blended into the polymer to give the compound its electrical conductivity and EMI shielding properties. Later in the webinar, we'll get into some of the specific criteria for choosing the binder and filler combinations.
Yeah, and it's important to note, Ben, and not always obvious to everyone, but if you're planning on using a conductive sealant or adhesive, there must be some electrical properties driving the requirement. So if that's not the case, you can just simply use a non-conductive.
And just as a note, throughout this webinar, you'll hear us refer to electrically conductive sealants, gap fillers, and adhesives collectively as compounds, conductive compounds, or specialty materials.
All right, so today we're discussing two of our types of electrically conductive compounds, one being adhesives and the other being gap fillers like caulks or sealants. So, choosing between an adhesive or a sealant is a pretty simple and driven by two factors. One is bond line thickness and one is lap shear strength. So basically, do I need to glue something that I'm never going to take apart again, or am I doing something like sealing the seams to keep dirt, dust, and rain out in EMI? And we also wanted to mention that these classifications of what differentiates an adhesive versus a gap filler are very specific to Parker Chomerics, and this is just the terminology that we use to help distinguish products for our customers. So you may have heard it described in other ways in the past, but that's the differentiation we're making today.
Here's a graphic for some of the visual learners on the webinar today. Basically, adhesives are used to hold parts in place and typically work in very thin gaps, whereas sealants are used to fill larger gaps between those parts. Sealants may not necessarily be strong enough to act as adhesives, but if used in conjunction with mechanical fasteners like screws, they may work just fine for your application. And in addition, most sealants can be removed using a solvent to soften it up with very limited damage to the housing. So now we'll dig down deeper into some of the factors to consider for the design.
So when you're initiating a design that may need a conductive compound, first you want to consider whether or not you need EMI shielding, grounding, or both. Then you narrow it down next for the corrosion resistant aspect of it. So these should be the first properties that you look at because, you know, it's critical to the functionality of your design and as well as the long-term performance. So while these aren't the only considerations to note before you down select your compound, as you can see from the chart, we do feel that these are the first ones you should consider.
So other factors like bond line thickness, flexibility, lab shear strength, and the substrate have to do with the interactions of the compound and the parts that it is mating to. So let's get into some of those mechanical considerations now. Lab shear strength is the property that measures how strong of a bond the compound will have between two surfaces and is usually driven by the binder itself. So for example, in general, epoxies will have a much greater lab shear strength than silicones and polyurethanes. Because of this, they're characterized as adhesives instead of gap fillers. At the same time, silicones will vary in adhesive strength and can be considered both adhesives and sealants depending on strength of the bond.
Next is bond line thickness. It's a major concern for stack-up tolerances as well because these materials are highly filled with metal particles and you can't get down to that ultra-thin gaps. Some of the softer materials like copper, you can actually crush or morph the particle if you compress too hard. Many adhesives work much better where bond lines are thin and the tolerances are tight. Different particle morphology, also known as size and shape, will have an impact on that minimum bond line thickness. Think flakes of material can lay flat versus a round particle that cannot.
And lastly, flexibility of a material when it's cured is important to consider. Vibration and quick temperature changes leading to uneven thermal expansion or contraction of the parts means that maybe a more flexible material would be needed. Epoxies tend to be brittle and crack in high vibration settings, whereas silicones are far more compliant. Some materials like polyisobutylenes will actually never cure and will create a great electrical bond where parts may see a lot of motion. We also want to mention that many of these material characteristics are generalizations. So there are new materials being developed every day and hybrids used for all kinds of applications. For the purpose of this webinar, we're really speaking at a higher level for most of this content.
So as we mentioned, the electricals are the main reason for choosing the conductive compound over a non-conductive. And the electrical properties come from that conductive filler that are mixed into the binders. And it's an important step in your electrical considerations. Remember, we had discussed grounding versus shielding. You know, it's the first question. If you look at something like a silver or copper, they're very good conductors of electricity and inherently more electrically conductive than, say, nickel or graphite. Therefore, it makes it a better grounding option. However, across most frequencies, a nickel-plated aluminum particle will have a higher EMI shielding level than a silver-plated aluminum because of the inherent absorptive properties of the nickel. So Ben, does high conductivity always lead to high EMI shielding?
It certainly does not. And I want to repeat that for emphasis. EMI shielding is not always driven by the highest particle conductivity. While conductive fillers will have high EMI shielding, other properties that impact shielding are things like particle bite through, particle shape, particle size, and paramagnetic or ferromagnetic properties. Sierra, what does bite through mean?
Bite through refers to how well the particle can break past coatings and make a solid electrical contact. So geometric particles and flake-shaped particles will have better bite through than a spherical particle. And galvanic corrosion is caused when these materials with different electrical potentials interact in the presence of an electrolyte. So basically, dissimilar metals can be eaten away or dissolved. So finding materials that interact well is crucial in exposed applications. And for further details actually on limiting corrosion, Ben and I did a webinar a few months ago. So if you are interested, you can look at that corrosion webinar on our website.
When you're thinking about the lifetime of the assembly and dealing with the compounds, you should also think about how strong of a bond you're going to need. When using adhesives, you will typically get a permanent bond that's going to need a crowbar or a pickaxe or a jackhammer to get the plates or the enclosure apart. Using a sealant will allow you to soften it with a solvent and potentially get the parts or potentially get the housing apart with a little bit of work.
And this applies to rework and field repair as well. It's really important to know what the future of this part looks like. So if the parts need to be taken apart for field repair every 5 years, a very strong epoxy-based adhesive is probably not going to be your first choice. If field work is required, do you have to completely remove the sealant, or can just a small section be repaired by itself? Is there special equipment needed to remove and redispense? You know, if this is a heat cure system that requires an oven and you're climbing a radio tower to repair it, these are very important questions to ask yourself.
Yeah, I mean, when you're also thinking about sealing, you should think about what level of sealing or what environmental conditions the compound will be in. So for example, do you need to meet a specific sealing specification such as an IP rating or a NEMA rating? Do you need to meet a hermetic seal or a long-term airtight seal? As we mentioned earlier, polyisobutylene is one of the compounds, and it actually has a very low gas permeability and may work pretty well in those applications. In general, silicone-based sealants are probably the most common and will give an excellent environmental seal as well as pretty good flexibility.
All right, we just wanted to briefly touch on the difference between conductive and non-conductive materials. So non-conductive materials are often much easier to work with, as the conductive materials may be more particular to proper mixing. You really want those particles to mix evenly in the material. And also galvanic corrosion is not a concern with non-conductive, obviously.
Conductive materials need to cure properly, not only for the mechanical properties like non-conductive materials, but also for the electrical ones as well. So a full cure is typically needed to get the adequate shielding or grounding needs. And if you think about it, replacing some of the binder or the base material with a metal filler will actually have an impact on the hardness of the material itself. And finally, some conductive compounds are actually limited in bond line, both on the low end by the size of the conductive particles, like Sierra mentioned earlier, and also on the high end, just to make sure that you're getting a good electrical contact throughout.
I've said it before, it's always, it can be much easier to think ahead and design for a conductive sealant. And then if you don't need it, then switch to the non-conductive, just because of some of the challenges in working with metallically filled materials. You know, I've had customers using a non-conductive adhesive with a very thin bond line, little real estate, that eventually fail their EMI test. And then all of a sudden they identify the need for a conductive adhesive. Now your problem is, you know, you have a 2/1000 gap and you're trying to dispense a minimum of 7/1000 thick adhesive. So it's not going to work out well, as you can probably guess. I do give the same advice for design of EMI gaskets. It's better to know it and then not to need it than to need it and not to know it. So just consider you may end up needing a conductive after all.
So now let's get into working with the conductive compounds and what it takes to dispense them. And as Jared mentioned earlier, don't forget there will be a question and answer session after the presentation. So feel free to submit those at any time during the session.
All right, so before you order your conductive material, you need to know how the materials can be stored, how it's going to show up on your shelf or onto the doorstep here. Shelf life can be pretty varied for materials. You need to know how long you'll have until the materials expire and they won't meet those original specs. So also some compounds need to be stored in frozen or cryo conditions to slow down the curing process and prevent from hardening before it's applied, meaning you're not going to be able to ship these ground on a Friday over a holiday weekend on dry ice. But if you did your homework and you've received your frozen material, then you would now need to be defrosted, and you can either do that at room temperature or in a warm water bath to bring that temperature up to which they can be worked.
At the same time, while your compound is defrosting, the substrate may need to be prepped so that the materials adhere well for both mechanical and electrical properties. Some materials will need primers or adhesion promoters to prepare the surface and make sure that the compounds stick well. Surfaces should always be cleaned, and oftentimes may need to be physically roughed or chemically etched so that the materials, adhere well. That can include sandblasting, sandpaper, or even wet sanding, as well as some of the chemical etching with dilute acids. Flame treating and oxidizing the surfaces, as well as conversion coatings, will help reduce a lot of that electrical contact resistance where the two materials are mated together. And finally, corona surface treatments, or actually arcing of the material, will align the charged particles on the surface of a material and encourage strong adhesion, but should really only be done very shortly before the application for best results.
Okay, so what about the steps to dispensing, and what does good dispensing look like? All compounds and adhesives should be checked for special health and safety guidelines. Do you need venting in the area where you're working? And while most have pretty low volatile content, or VOCs, you still may need a well-ventilated area and a proper way to dispense the material if they're hazmat classified. Ben, what kind of format do these materials come in?
So most conductive compounds will either be one component or two component. Two component compounds will usually have the main binder and the curing agent separated until they're ready to use. Most adhesives and sealants will have a consistency somewhere between a pretty free-flowing liquid all the way up to a thicker, grittier paste, or somewhere in between. When you're looking at applications, vertical surfaces and overhead dispense applications will most likely need a thicker paste that does not drip or run. Sierra, what do I have to know about packaging and mixing the materials?
So most two-part materials, if it's a one part, it's coming in a tube, you're going to dispense it. But most two-part materials will have to be mixed properly, and that usually happens within the package or the cartridge. So while some dispense equipment can be dispensed by hand, like a syringe, others may need equipment like an application gun or a pneumatically controlled system with a foot pump. Ben, are there any types of systems to avoid or steer clear of?
Because we want to minimize the damage to the particles and protect the plating on the metal particles that give us that good electrical contact, we urge customers to stay away from auger valves or auger style systems that can actually shear the material.
Good to know. So when you're dispensing, you have to know the working life of the material and how long you have to manipulate it before it starts to cure or harden. Some materials use cure systems like acetic acid cures, and they have a very short working life in the range of just 5 minutes. Others will give you more time to smooth the material onto a flange or connect the two mating surfaces together. There's a few definitions to know when working with conductive compounds. One is tack-free time. And this is the time it takes for the material to develop a skin so that it's no longer sticky or wet on the surface. And this is also referred to as a cure time to handling. And the second is full cure. When we refer to a full cure, it means the amount of time it takes to develop and complete mechanical and electrical properties as presented in the data. Benner, what are the 3 different types of cure?
There are 3 different types of cure mechanism, or the way in which the products will cure. The first is known as room temperature vulcanization, and it actually involves the use of a catalyst like platinum that's combined with the binder system, and that facilitates the cross-linking and the curing of the material. The second mechanism is known as a moisture cure. This means that the material will cure as a result of the ambient humidity and moisture surrounding the material. Some things to consider are that the cure times can be impacted pretty significantly by the environment. So for example, a moisture cure system will cure much faster in the middle of the Amazon rainforest than it will in Phoenix, Arizona. The other type of cure is a heat cure system. This means that the binder will cross-link as heat is added to it. In most cases, the higher the heat, the faster the cure, but there are obviously upward temperature limits. Some materials will cure at room temperature just fine, but adding heat will actually speed up the process. And a very important note, for heat cure materials, the highest recommended cure temperature is usually the one that will give the best mechanical properties.
All right, so this slide, we wanted to describe the difference between 2 types of materials, one a thermoset and one's a thermoplastic material. We have both types in our conductive compounds portfolio. A thermoset is a material that strengthens as it's heated, but cannot be melted or reheated after initial cure, whereas thermoplastics can be without any chemical changes.
And the other definition on this slide that we wanted to touch on is glass transition temperature, oftentimes abbreviated as TG. Glass transition temperature not to be confused with the melting point of the material, is actually the point at which the properties of a thermoset polymer will transition from rigid and glassy to flexible and rubbery. So some materials like silicones will have a very low glass transition temperature in the negative 80 or lower Celsius, and are meant to be used above their glass transition temperature so they can exhibit those flexible properties. Others, such as epoxies, will have a very high glass transition temperature, meaning that at most operating temperatures, they're meant to be used in a glassy and rigid state.
So after adhesives and sealants are applied, they may actually need to be painted over or sanded to match the aesthetics of the application or for aerodynamics. So usually a primer is needed before painting. And in some cases, like with silicones, you need an extra layer such as a polysulfide system to get that paint and primer to stick well to it. Airframes are a perfect example where the materials would need to be sanded down because of aerodynamics. Also referred to as a fairing material. That material would require sanding before final paint to make that surface smooth and free of defects.
Our last section before the application examples is all about testing and validating of the material. So volume resistivity, shielding effectiveness, lap shear strength, and peel strength are the key properties that most people will test for or design around in order to validate a program requirement. Each of them typically has a different test procedure and often an industry spec surrounding it, such as IEEE, ASTM, or a military specification. So this slide shows a few of the different electrical tests that can be done on compounds, including transfer impedance and volume resistivity. So on the left side of the slide, you'll see the SAE setup for transfer impedance that actually applies beads of adhesive along an aluminum test plate or a couple beads of sealant along two outside arcs on those same test plates. Volume resistivity on the right side is measured using one of a couple different ASTM specifications. So this is actually the standard IEEE shielding effectiveness test, where the conductive compound is dispensed on a metal plate in between two shielded rooms. So Chomerics does have test facilities, and we have a number of shielded rooms where we perform not only testing on our own materials, but also the overall systems and EMI testing for our customers' electronic systems. The left shows a standard frame test, and the right shows a slot test. Each of these tests can be run along the entire frequency spectrum. So from the kilohertz range all the way up to 18 gigahertz, and in some cases, even 100 gigahertz for military qualification. It's also important to note that these tests are run before and after environmental exposure to get an understanding of how the materials will perform.
Thanks, Ben. And really one last note on that slide, the slot material evaluation is more of a material evaluation versus where the frame test is more of an application specific test and can give you higher shielding values. Thanks.
So mechanical testing actually uses the adhesives and sealants attached to a couple different aluminum test panels that are pulled apart until the breaking point, and that's per the specific test procedure. The force that's recorded at that break is measured and then recorded as the lap shear force.
Yeah, and as Ben alluded to, most of these materials are also tested on how they would hold up in harsh environments. So environmental testing can include high heat, high humidity testing, as well as salt fog testing to validate that the conductive compound will maintain its mechanical adhesive strength, its electrical properties. Obviously, we're trying to minimize galvanic corrosion when exposed to these environments without the additional protection. Low temperature testing is also done to make sure materials will operate after low temperature storage and in cold environmental operation. This is important for all kinds of military applications, such as high altitude and shipboard programs. And after environmental testing, the parts are all run through the same transfer impedance, shielding effectiveness, and mechanical tests, and those values are recorded. Okay, so conductive compounds can be used in a variety of ways, which we'll show you now. But keep in mind, these can be used in field repair to close joints and seams, to repair conductive gaskets that may have torn. You can use it as a fastener fill. People are literally dipping rivets in this stuff. You can fill large or small gaps. You can cold solder components to circuit boards. I mean, the possibilities are endless. So let's take a look.
So the first application and case study that we're going to go through is actually on a night vision camera assembly. In this case, the customer needed an EMI shielded and permanently sealed housing that was mounted to the optical system. So what they did is they used a electrically conductive coating to shield the plastic housing, and then a conductive elastomer gasket for environmental sealing. But the last step was that they actually needed to ground the two housings together effectively. And this was done by dispensing a small drop of a 2-component silver-filled epoxy. So it was going to give them very high conductivity and therefore good grounding, as well as that very strong bond.
So this application for a military airframe needed a filling and fairing compound over a very large area in which every seam was caulked. There were a number of issues with vibration, as you can imagine, thermal shock and expansion, tremendous expansion and contraction of the airframe components as the helicopter was exposed to extreme environments. The sealant needed to be painted over, and it would be applied in overhead and vertical areas of the aircraft. So the 2-component polyurethane binder with a stabilized copper was a perfect solution. An added benefit was that the polyurethane developed a full material properties in less than 4 hours with an elevated cure schedule. So the aircraft downtime was significantly reduced. So yeah, this was a good application.
And the last case study we're going to go through is actually for a large transport container carrying C4I command and control and communication equipment. So a conductive compound was needed to bridge the large gaps between the metal frame surfaces. So as you can probably imagine, this container saw a lot of very heavy shock and vibration along its journey. The doors and the connector ports were actually gasketed with either metal fingerstock or conductive elastomers, but all of the large seams still needed to be sealed for water and EMI. Because of the tolerance stack up, a sealant with a larger bond line was used. And in this case, it was a polythioether because the fact that it would need to have been coated, and a silicone would have required that additional processing with a polysulfide before a primer and paint. Finally, a silver-plated aluminum particle was embedded into that polythioether. And the reason that it was used in this application was because it actually provides the best corrosion resistance on aluminum substrates of any compound filler.
And lastly, while this presentation has been an overview of conductive sealants and adhesives, we just wanted to highlight some of the Chomerics products within the product family. You know, we control the development and the formulation of these compounds and fillers, and are quite often developing new materials based on customer specific requirements. All of these applications examples are shown. Many of the standard products were a result of material development driven by our customers. So, you know, simple modifications can include VOC content or application methods. You know, there's different ways we can kind of make these materials a little different if you need something. So if you have a custom application, please reach out.
And so with that, we're going to start getting to some of the questions that you all submitted. Please, while we're answering questions, please continue to answer them. If there's questions that we don't get to through the session, just know that we will reach out to you personally with answers. And let's get right into it.
You want to start us off, Ben?
Sure. So a question that we have from Perry is, are there any major chemical incompatibilities that you are aware of that would cause issues with applying a Chomerics conductive sealant and another sealant to different places on a part simultaneously? They would not be in contact in this scenario. So I did want to note that for these questions, we also have Brian Flaherty, our product line manager, answering some of them. So Brian, I guess in this case, you know, are there chemical incompatibilities that would cause issues with either Chomerics conductive sealants or other sealants that you've seen on the market?
Yeah, I think you have to be careful, especially with like platinum cure silicone systems. Sulfur is one contaminant that's known to kill the cure of these materials. There are other materials though that kill the cure of silicone materials. Fatty acids can also kill the cure of platinum cured silicone materials. So yeah, you must be careful when you're using multiple or two different type polymer systems with different types of cure systems on the same part, it is something that you want to make sure that there's no interaction between the two systems.
Okay, so I have a question from Jacob. What is flame treating? And I also have one from Alfred. Is corona treatment the same as plasma cleaning? So maybe you can describe the difference between those flame treating, corona treatment, and plasma cleaning, Brian.
Yeah, so flame treatment is the use of a gas flame right against the surface of the part, and they all aim to accomplish the same thing, and that's increase the surface energy of the part and improve adhesion. Plasma treatment usually requires a high energy gas in a vacuum type environment. It's more of a batch process, but that's also very effective in increasing the surface energy of plastics. And corona treatment is the application of a electrical arc on the material, on plastic material again. This can be done in an atmosphere. In regular atmosphere, it doesn't require vacuum. And this is usually done right before you intend to cure the material onto the part. With all of these treatments, you want to apply the adhesive right after these treatments because over time, the surface energy will decrease and the advantage of the gains that you get by using these surface treatments will be reduced.
So the next question we have is from David. He asks, for the gap fillers, how do you spec out the electrically conductive fillers, particle size, shape, surface area? And I guess as a quick input, typically a lot of that is depending on the application requirements and some of the program requirements that are driving the use of those fillers, whether there's a high EMI requirement, whether there's a bond line requirement or a specific EMI shielding level. And then working at how those fillers are combined into different polymer binders.
Yeah, I think so. So those three, particle size, shape, and surface area. Chomerics does significant testing on our conductive fillers to understand exactly the size. Typically, we use microtract and do a particle size distribution because most of these particles, you don't get one particle size, right? It's usually a particle distribution for these different conductive fillers. And the shape also has a huge impact on how it's going to perform in an adhesive or in a sealant. One of the things that, over years and years of testing and analysis of our conductive fillers, we found out that, you don't want to design in a spherical particle for any application where you might see a lot of vibration, like a rotorcraft or an aerospace type application where you might see a lot of vibration because typically when you vibrate conductive particles that are spherical shape, the electrical performance of the shielding will degrade.
Okay, so we have a question from Todd. What effect does high number of thermal cycles have on RF performance? Specifically, we're looking at performance from 1 to 40 gigahertz and hundreds of cycles from -55 to 105C.
Yeah, so that's a good question. That is something that Chomerics has the ability to characterize in-house. We put a lot of our materials through thermal cycle testing, and we test shielding before and after various thermal cycles. It usually has a lot to do with the type of material and also the substrates, how closely the coefficient of thermal expansion is between, the substrate that you're applying the compound to and the compound itself has a lot to do how it will perform after thermal cycling. But other things can influence, how well it shields following thermal cycling, like, particle size and particle shape and filler loading. So there are several different characteristics that go into that, but it is an important test to run, and it is very specific to the substrate that you're going to put these materials on.
The next question comes in from Todd. He says that silicone is problematic in many of our factories. What is the best alternative for RF performance?
So I would question, what he means by silicone is problematic. Usually when I hear silicone is problematic in their factories, it usually has to do with they have coating operations in their facility, and they're worried about silicone contamination and, you know, the fish eyes, which is, you know, anytime you get silicone contamination in a coating, when you go to spray that coating, a lot of times you'll see this surface phenomenon, which, you know, people refer to as fish eyes, and that's silicone contamination in the coating. The best thing to do if you're looking for alternatives to conductive silicone materials, one potential alternative is our conductive polythioether materials. Chomerics has a Cobond 1018 and a Cobond 1019, which are conductive polythioether compounds. And the nice thing about these materials is that they're paintable. So in addition to not having to worry about silicone contamination, these materials accept coatings very well. And typically you don't need a primer, but if you do need a primer, typically you don't have problems with getting that primer to adhere to the polythioethers.
Okay, thanks, Brian. And if you go to slide 29 too, there's a couple different types of non-silicone materials there. So we have a question from Thomas. At the end of slide 18, you mentioned that the max recommended cure temperature was based on what would give you the best mechanical properties. Perhaps I missed the discussion on this, but do the electrical properties also vary with cure temperature?
So yeah, one of the things that you'll notice on our specialty materials selector guide is there's a little footnote that says the mechanical and electrical properties reported for typical properties are properties measured at using the highest temperature cure schedule that Chomerics recommends. And that's because with a lot of these cross-linking systems, you typically get a more dense or tighter cross-link at the higher temperatures, and that's what gives you the better mechanical and electrical properties.
So a question we have from David is, what are the ways used by Chomerics to provide electrical property stability for the silicone gap fillers? And does it vary based on the filler composition?
I'm sorry, can you repeat the question, Ben?
Yeah, so what are the ways in which we provide electrical property stability for our gap fillers? And does it vary depending on the filler composition?
Yes, it does. So we do, as I mentioned earlier, we do a lot of characterization on our fillers themselves, right? So there are, in processing of our fillers, there's a lot of things that we do to help minimize the growth of or oxidation of our fillers over time. So a lot has to do with the way we plate and heat cure and treat our fillers that go into these conductive compounds. We also do a lot of formulation DOEs and sensitivity DOEs. I mean, if you look at the typical conductive sealant volume fill versus conductivity curve, it's usually what they describe as like a knee. And the worst thing to be is for a conductive sealant or material to be on the knee of the curve, you know, where it's, you know, if there's any change in that conductive filler, you know, whether it's, you know, surface area, particle size distribution sways one way or other, it has a huge effect on the electrical properties of the final compound. So what Chomerics does is, you know, upfront, they do a lot of formulation sensitivity DOEs to make sure that we're not on the knee of the curve, and that, you know, any change in filler, whether it be surface area, particle size distribution, will not affect the electrical properties of that conductive adhesive or sealant.
All right, we have one from Stephen, and I just lost it here. Okay, please expand on outgassing properties. What approaches can be used to select adhesives with low outgassing? And I guess I'll add on to that. Are there anything we can do after the material's applied to help with outgassing?
Yeah, so really, if you're going to develop a material that has low outgassing, you need to start up front, right? I mean, it starts back at the polymer selection, right? So you need to be using medical grade or low outgassing polymer systems to start. Then there's some additional things that you can do from a formulation standpoint, as far as minimizing the amount of volatiles that you add, whether it be rheological modifiers or solvents that you may add for flowability type purposes. The way, typically outgassing, Chomerics tests the NASA outgassing E595 standard is what we use to test our materials to. I'll be honest with you and up front that Chomerics hasn't developed a lot of low outgassing materials in the past, but it is something that we could do going forward. We haven't been asked this question a whole lot. I know with the increase in space applications that are being developed these days, we'll probably get asked more and more going forward, but we haven't done a whole lot to this point.
So one of the next questions is specific to one of our products. What are some applications where we'd see the use of polyisobutylene electrically conductive sealants? So specifically our Cobond 4660 or 4669.
Yeah, so typically those materials have been designed in applications where you're going to see a lot of vibration. So, mobile shelters, things that are going to be moved around on the back of trucks and may encounter a lot of vibration. Our 4660 and 4669 thermoplastic materials, they're actually solvated and do not cross-link. And by not cross-linking, they remain tacky and have this flexible nature to them that is really good and maintains good electrical conductivity even through vibration or vibratory applications.
All right, so we've got a question from Stephen. Has anyone requested or considered using conductive sealants as a thermal gap filler for electronics? I assume that the thermal conductivities of conductive sealants are far better than non-conductive gap fillers. Certainly care would be needed to make sure conductive sealant would not become thawed. The answer is yes. Conductive materials have metal fillers in them, so inherently metal is a conductor of thermal. So we actually do have some published values on some of our electrically conductive materials as far as thermal conductivity goes. But you'd be surprised. There are some very technically highly filled ceramic thermal materials that get into the 7.5, watt per meter K range, whereas some of these may be in the 1 to 2 to 3 watt per meter K. I don't know if you have anything further for that, Brian.
No, that was well said.
Okay, cool.
So one of the questions is about our fillers. When we list it as a silver aluminum, is that a silver over aluminum or aluminum over silver? To answer that question, it is a silver plated aluminum particle. So the silver is on the outside. As you'll see with most of our fillers, the outside is either a silver or a nickel plating over an aluminum particle, a glass sphere, potentially a copper or a graphite particle as well.
All right, a question from Timothy. Over time, is there degradation of conductivity due to oxidation of particles? And I believe the answer is yes. Brian?
Yep. Yeah, certainly with some of the silver-plated copper materials, there can be some degradation over time and oxidation over time, especially when you get to higher temperatures. So, if you're looking at, some of the silver-plated copper materials, you may want to look at the high temperature limit of those particular materials. The other thing that Chomerics does in some instances on some of our silver-plated copper particles, we actually have organic coatings, or we have other stabilizing surface treatments on those copper particles, which helps to reduce the oxidation over time. So while it is true that there are some silver copper particles that may show degradation over time, especially at higher temperatures, specifically oxidation, there are other silver copper fillers that Chomerics has that don't show that same degradation. So it's really specific to the filler itself.
We have a question from John who asks, is there a gap filler that is fairly easy to rework that could be used, say, either as a replacement or an augmentation to a current molded seal, such as a conductive elastomer?
Yeah, so it really depends on the application and what your tolerance is and how you define easy. I think some of our silicone Gap fillers, the moisture care silicone gap fillers like our Cobon 1075, 1016, 1038 type materials certainly can be scraped off and cleaned off a substrate using toluene. Same with some of the polyethyl ether materials, Cobon 1018 and 1019. But it really depends on your particular application and what you consider easy, I guess.
Okay, so here's a question from Alejandro. Is there a way to measure resistivity for inline production? Something not as technical as a 4-point probe or the setting you had there in your slide with the IEEE test method?
Yeah, so I think the best way to measure it and what kind of simplifies it is the 4-point probe method using Chomerics' co-probe, right? I mean, Chomerics sells the co-probe that 4 wires insert to very easily. And I think, you know, for $250, I think you can buy a Chomerics co-probe and a handheld ohm meter and be able to get pretty good electrical values of your conductive adhesive or sealant in line on the production floor.
As you can see on this slide, the co-probe is actually the photo furthest on the right, and it is aligned with the ASTM D991 specification. The next question comes in from Timothy. In terms of galvanic corrosion, let's say my substrate and conductive filler are beyond the recommended limits on galvanic compatibility in normal circumstances. Should I be concerned with galvanic corrosion on either the substrate or filler? I will say that in a lot of our galvanic corrosion testing, we've done a number of tests on our various fillers, both in conductive compounds and conductive sealants against a number of different substrates, whether those are conversion coated aluminum, steel, stainless steel, magnesium, things like that. So with application specific examples, by all means, please feel free to reach out to us when it comes to potential galvanic corrosion and compatibility. Brian, I don't know if you wanted to add to that.
Yeah, the only thing that I would add to that is anytime that you have a difference in electrical potential between the conductive filler that's in a sealant or adhesive in your substrate, there's an opportunity for galvanic corrosion. Chomerics does have some compounds. The Coshale 2000 series coatings, for example, have a hydrophobic polymer system that they've been designed with. And that polymer system actually keeps moisture away from the surface. So without moisture, you don't have your electrolyte, you don't have galvanic corrosion. So there are some exceptions, right? If you have, you know, coatings like the Coshale 2000 that are designed with hydrophobic polymer systems, they keep out the moisture, and that helps to reduce the galvanic corrosion by eliminating the electrolyte or the water in the air.
Okay, we've got a question from Stephen. Do any of your conductive sealants or coatings lend themselves well to corona suppression as applied to rough and or protruding metal objects? And I'm not sure how to answer that.
Yeah, I'm not sure I understand the question. That may be one that we have to take offline.
Yeah, Stephen, feel free to reach out to us and we'll get a better understanding of what you are trying to ask.
Yes.
A question from Todd refers to hermetic modules and hermetic sealing. When not within a hermetic enclosure, some of the products are exposed to terrible conditions like salt fog, jet fuel, low pressures, high temperature swings, vibration, and a 30-year lifetime. Are there any suggestions for keeping out RF covers in place? So I guess in that case, we would look at potentially combining conductive compounds with some of the other conductive solutions. So as Brian mentioned, things like conductive coating that may help in terms of sealing off those surfaces and providing a longer life cycle. Additionally, using a conductive elastomer gasket to keep out a lot of the jet fuels and the salt fog may help protect some of the internal components, just because some of them are designed for those harsh environments and long lifetimes.
Okay, we have a question from Jacob. What would you recommend for bonding conductive neoprene pads or conductive UHMWPE to steel or aluminum. This would have to be spread over a large bonding area. So neoprene to steel or aluminum.
Yeah, neoprene is a tough material to stick to. I'm not sure that anything that we have would stick. You may have to use one of our primers to get good adhesion to the neoprene itself. I don't worry so much about the aluminum surface. You know, we stick to aluminum all the time, but you may have to use some sort of primer with our conductive materials to get good adhesion to the neoprene.
Good point. Primers.
And I guess building off of that, do we have information about adhesive strength relative to from our conductive compounds to various plastic materials, whether that's a polyethylene, you know, a PVC, things like that?
Yeah, so we do have some data over in our applications lab. The problem is that there's so many different types of grades of plastic. You know, even if you talk about a polypropylene or a polycarbonate material, then they have different glass fills and they have different grades. So it's really very specific to that particular grade of plastic. You know, we have some data that we can share, and I encourage you, if you have questions about how a conductive material that Chomerics makes sticks to a particular grade of plastic, I encourage you to reach out to our applications department and see if they have any data. But chances are we don't have data to that exact grade of plastic, but we may have some data to something similar, and we can give you a good idea of whether, how successful you might be.
So I will say that we're getting towards the end of our allotted time slot. So we're just going to take one or two more questions. Again, as a reminder, if we haven't answered any of your questions on the webinar here, we'll be sure to reach out and make sure we talk to you about your application specifically.
Yeah, and just to reiterate to David, and there was a couple other people that asked, these slides will be provided within 24 hours. They're going to be posted up on our website. I believe they're on YouTube, especially along with our corrosion presentation and gasket, elastomer gasket. This is Ben and I's, 5th or 6th webinar now. So these will all be available at a later time if you had, coworkers that couldn't make it, or you just want to have it as a reference point.
So probably our second to last question comes in from John. Would the dispense equipment for some of these products be usable on the same line dispensing gap fillers for thermal management or other types of materials?
He's asking about whether conductive sealants or adhesives could be dispensed using similar equipment, or
correct,
on the same line?
Yeah, exactly. So different packaging and different dispense applications.
Yes, I think in general the answer is yes. I mean, obviously it's equipment specific, so we'd have to understand what type of equipment you're currently using. But some of these materials could be dispensed using, if not the same equipment, similar equipment. It may require a different dispensing valve to have flow control and to be able to dispense the size and shape that you want, but they can probably be mounted on the same gantry.
All right, and one more from Annie. Can the ProShield application dispensing guns be used for Cobond materials, the 6 fluid ounce Semco cartridge?
No, the ProShield materials are packaged in an EFD Semco tube and not the standard an EFD plastic tube, excuse me, instead of the standard Semco tube, which the CoShield materials are packaged in. So that gun will not work for our CoShield materials.
And with that, we are going to end this webinar. But again, thank you all for joining, for submitting your questions. We hope it was valuable to you all. You have the contact information for myself and Sierra as well. So by all means, please feel free to reach out to us with application-specific questions. And once again, look out for our next webinar. It's in the same family, but we're going to be talking specifically about electrically conductive paints, coatings, and inks. So thank you all very much.
Thanks, guys.